Okay, in this session we're going to be looking at exponential functions using what we call the natural base e. E is a number, much like pi, that is irrational, and it's looking at the formula 1 plus 1 over n to the n power. Okay, and what does this thing do as n goes to infinity? So as n goes to infinity, what does this equation actually do? So to simulate that, we are going to look at plugging in these values into our calculator and see what you get out for y. So what I want you to do is take a minute and do that and see if you agree with what I have. So for the first one I got 1. For the second one I got 2.25. For the third one I get 2.37. For the fourth one, I got 2.44. For the fifth one, I get 2.488. Now remember, you hit Control Enter to take it from fractional form to decimal. For the second one, or for this one here, 1.1 plus 1/10 to the 10th power, I get 2.594 if I round. Then I get 2.705 again if I round. And for this last one, I get 2.717. So if I were to continue and let that exponent and the denominator in this fraction get bigger and bigger and bigger, okay, this equation is going to approach the number e. Okay, e is approximately, and that's this number down here, the 2.7182818, and so on and so on. It goes on forever, which means it has no pattern, just like pi. So that's why we call it an irrational number. Okay, so, and it has a lot to do with the compound interest stuff that we were doing in the last section, and we'll get back to that. All right, so how to simplify expressions and things with e. We're going to treat it kind of like an exponent, or like x to the third power times x to the fifth. So we're going to treat it like a variable with an exponent, but knowing that it's actually a number. So e to the third times e to the fifth, I'm going to add those exponents to get e to the eighth. This is what we call my exact answer, because if I hit Control Enter in my calculator, it's going to give me a decimal that is rounded. For b, 12 divided by 3 is 4, and when I divide like bases, I subtract the exponents, so that gives me e to the first. And raising a power to a power, I give the power to everything in the parentheses, so that's 5 squared, which is 25, and then e to the negative 6x. Remember, negative exponent means 1 over, so we're going to move the e to the 6x to the bottom. The 25 is not raised to the negative power, just the e stuff is. Okay, now to get your calculator to approximate values, you're going to hit Control Enter. Your e button, if you look on the left side, there's an e to the x button, so I'm going to hit that button and then plug in the 4 and hit Control Enter. And I'm going to use my approximate symbol. So e to the fourth is approximately 54.598. E to the negative 0.09 is approximately 0.914. And I want you to try the e to the 5/7 for yourself. Okay, so these also have a graph associated with them. We've been doing exponential graphs as y equals ab to the x power. Okay, so now our b is going to become the number e. And in order to make us have a exponential growth or decay, before it was the base that did that. It was a number that was bigger than 1 in order to get to a growth function, and a number between 0 and 1 to get to a decay function. For our e, we have y equals a e to the rx. This, because e is always 2.718 and so on, and which is bigger than 1, I have to control the growth and decay by the exponent. So if I have a negative exponent, meaning this r value here is negative, I will have decay. If it is positive, I will have growth. And that's assuming that a is positive. If a is negative, it's going to take, say, this exponential growth. Okay, so, sorry, I got interrupted, so I don't remember what I was saying now before. So if the a value is negative, it's going to take this graph here, and it'll just flip it so that it opens down instead, and it's all under the x-axis. Let's look at graphing a couple of these. So if I have 3e to the 0.25x, my r value is this 0.25. It's positive, so that means I should have a growth graph. Okay, so I'm going to start with x equals 0, because that's going to make this 3e to the 0 power. 3 times 1 is 3. So I have a graph that's going to go through 0, 3. Okay, and just for space sake, because these graphs are so tiny for me, rather than plugging in 1 and negative 1, I'm going to plug in 4 and maybe negative 4, just because it's hard for me to graph. So I'm going to plug in 3e to the 0.25, and I chose 4 because it's divisible by 0.25. That's going to give me 3 times e to the first power. So that's going to be 3e to the first power, Control Enter, is 8.155. So if I go out to 4, I'm going to go up to 8, and it's just barely bigger than 8. If I plug in negative 4, it's going to give me a negative 1 in the top. If I plug in, so that's going to be 3 over e, so 3 divided by e to the first power is 1.1 essentially. So my graph is going to do something like this. Notice with the graphs that we were doing before, where the base was a number other than e, we still have a horizontal asymptote. There's nothing I can plug in for x that will magically make this 0. So the graph still approaches y equals 0. That's still my horizontal asymptote. My domain is still all real numbers. I can plug in whatever I want for x. And my range is 0 to infinity, just like it's been in the past, not including 0 because the graph will never actually equal 0. Okay, and we can still shift the graphs as well, left and right, up and down. We can change the horizontal asymptote by shifting it up or down. So this +1 for the second graph is going to shift my y-intercept, or my horizontal asymptote up 1. All right, now to make my exponent for e equal to 0, let's change colors here. To make this up here equal to 0, I need to plug in x equals 2. So I'm going to plug in x equals 2. So that gives me e to the 0, which is 1, plus 1 is 2. Okay, and again, for lack of, I want these things to be kind of spaced out so that I can see because my graph is so small. I'm going to plug in x equals 4 again. Okay, so if I plug in 4, I get e to the negative 0.5 times 4 minus 2 is 2 plus 1. So I get e to the negative first power plus 1, which gives me 1.37 if I round. So if I go out to 4, I'm just barely above 1. Okay, if I go to 0, if I plug in 0, I get e to the negative 0.5 times negative 2 plus 1. So e, and negative 0.5 times negative 2 is 1. And then plus 1, Control Enter, gives me 3.72. That's here-ish. So I'm going to get a graph that does something like this. It's going to approach the y equals 1 but never actually get there. Alright, so I said that we can use this for our compound interest. So we've looked at ones that had, so we did the p times 1 plus, and r over n to the nt power, right? Gave that back in the beginning, right here. Okay, we did that in the last one, where n was how many a year, n was the number of times that the account compounded in a year. R is the rate of whatever your bank account, your interest rate is. So if n goes to infinity, okay, so that means it's continuously compounding. So that's looking at this equation. Which, how do you even evaluate that? Okay, and we'd kind of simulated that at the beginning of this session here on this video. We said that this part of the equation goes to the number e. So our equation now becomes the amount in my account is my principal, what I start with, times e to the rate times time power. So if I deposit $8,000 into an account that pays 6%, which is 0.06, annual interest, and it's compounded continuous, what do I have in my account after 1 year? So I'm going to plug in 1. So I've got 8,000 e to the 0.06 power. And that gives me $8,494.69. Remember, we don't round up on the pennies. So what I want you to do for the next time is look at example 5, and I want you to decide, so you're going to calculate based on these two accounts, if I have $1,500 to invest, okay, and they compound annually, so that's going to be using the P times 1 plus R over N to the NT, and P times E, whoops, I don't need that little, for the second one. It's going to be PE to the RT for the second one. Okay, so you have a 5% annual interest that compounds annually, so you can use this equation with the $1,500, okay, or a 4.5% compounded annually, that's this equation. I want you to figure out how much money you'd have after 5 years, and then which bank account would you choose?